going to prove the second part of the fundamental theorem of calculus right now. So if you have a little g that's integrable, define capital G of x to be equal to the integral from a to x. So x is the variable. If you input an x, it's going to change the amount of area under g that you take. So a bigger x means that you get more g. You do x plus epsilon, you're not going to get much area. And that's defined for all x in the interval. Then g is, I'm going to prove it's uniformly continuous. And if g is continuous at a point c, then we can find, then g is differentiable, capital G is, and g prime of c equals g of c. So I'm going to prove g is uniformly continuous. So I'm going to start with, since g is integrable, little g is integrable, little g is bounded by m. By some capital M belonging to the real numbers. Okay, now I'm going to prove that capital G is uniformly continuous. Epsilon be bigger than 0. So I'm going to need to tell you a delta. Let delta equal something. Then if x and y belong to AB, such that x minus y is less than delta. I'm going to tell you what delta is in just a little bit. I'm showing you kind of how I prove it. I have g of x minus g of y. I'm going to need to prove that this thing is less than epsilon. But let's unravel the definition. Big G is equal to integral from a to x of little g. Nice integral from a to y of little g, which equals, if you just do a little bit of work with integrals, which, I suppose I may as well show you, ax of g minus a negative, I can switch the limits of integration. G equals the integral from a to x of g plus the integral from y to a of g. Well, if you go from y to a and then a to x, that's the same thing as doing the integral from y to x of g. And the absolute value of an integral is less than or equal to the integral of the absolute value. We know that. So now it comes in that absolute value of g is bounded by m. G is bounded by some m, so this is less than or equal to x times m, which equals, right, m is just a constant, m times x minus y. So that's going to be less than delta. And if I cleverly pick delta equal epsilon over m, then I get is equal to m times epsilon over m equals epsilon. So G, big G, is uniformly continuous. On AB. Okay, now I need to prove that if G is continuous at a point C, then G prime of C equals little g of C. So the way I'm going to do that is I'm going to set up the usual proof for continuity, and hopefully I'll have enough space to prove that something is, or to prove differentiability, sorry. I'm going to let epsilon be bigger than 0. I'm just going to set it up, and I'm going to have to go to a different screencast. Then let delta equal something. Then for all x belong to a, b, such that x minus c is less than delta, we're going to have, using differentiability, g of x minus g of c, the difference quotient at c. What's the derivative going to be equal to? The derivative is going to be equal to g of c, little g of c. So I'm going to have to prove that this thing is less than epsilon. But I'm going to do that in the next screencast. So, bye-bye.